Hello, my name is UiB-Keile Gavlen. I am from the Department of Mathematics at the University of Bergen, and I will tell you about the simulation analysis that we did of a hydraulic stimulation test at the Reykjanes geothermal field in Iceland. So I will first introduce the research team. This is really an interdisciplinary effort. So from the University of Bergen, there were Seyen Holdesdottir, Eva Stefansson and Inga Berre joined, all from the Department of Mathematics. Then from Norsa we had Laure Debuff, Anna Maria de Charante and Folke Øye. From Icelandic Geosurvey, Egil Gudnason and Christian Augustsson helped out. And then from our industry partners, there were Marcel Naumann from Equinor and Gudjon Eggertsson from HS Orca. To motivate the study, we need to consider the process of enhancing fault permeability by injections of fluids. So the target formations here are rocks where fractures and faults form the main pathways for fluid flow. Examples could be volcanic or crystalline basement rocks. Now, in this formation, one typically have a lower permeability than what is wished for from an operational setting. And the goal is then to manipulate the fault properties so that permeability increases. To achieve that, fluids are injected into the faults, and the fluid pressure will then work to push the fault walls apart so that existing tensions in the reservoir will make the fault slide. In this sliding, the fault walls will also dilate, enhance aperture, and thereby permeability will increase. On the surface, this sharing of the fault is manifest as induced seismicity. In terms of modeling, there has been studies that resolve the sliding process on individual faults in detail. And there has also been field studies which apply an implicit representation of the fault processes. What we set out to do was to try to simulate this process in a field setting and also resolve explicitly the processes on the sliding faults. At the University of Bergen, we have developed a hydromechanical simulation tool which is aimed at explicitly resolving processes on the faults in rocks and on the fault-rock interface. So the faults are explicitly represented in the computational grid, as you may see down here. Now, a bit more in detail, if these two triangles are cells in the computational grid, and the red line is a part of a fault that is in between, then the simulation model will have a notion of a fluid pressure inside a fault. There's going to be fluid flow in the fault. And we also measure the relative displacement of the two opposing fault walls. So with these tools, the process of sliding on the fault walls really becomes a frictional contact problem, which is very much reminiscent of the task of sliding an object on a table, which you might have done in high school. So our research questions were then, first, what does it take to set up a simulation model based on these principles to study hydraulic stimulation on a field case? And second, if such a numerical simulation tool is available, what can then be gained from the simulation, and what insights can be gained from the simulation results? So we focused on a test case at the Reykjanes Peninsula in Iceland, and the main effort turned out to be the population of the simulation model. So that entails fluid flow, rock mechanics, and mechanical interaction. And we needed parameters for the rock, for the fault, and the rock-fault interaction. Now, the latter two are things that you do not have to consider explicitly in simulation models that do not explicitly account for processes in faults and the fault rock interface. To give you some context, we're in Iceland. We're down at the very southwest tip here. Now, this is an area with a lot of faults, indicated by these the lines, colored lines in this plot. By various types of reasoning, we ended up with having 6 faults explicitly represented in the simulation model. They are indicated over here. We also see the path of the well down here where the injection was carried out. So we focused on a stimulation experiment that took place in late March 2015. This was in 2 steps. There was first a leak-off test, followed by an fluid injection at a relatively high rate, which was then aimed at enhancing the fault permeability. Important for this study, we have available both injection rates, so that is what goes into the reservoir, and concurrently seismic observations. So this is essentially the best idea that we will have on what happened, what was triggered by this injection. So for population of the simulation model, we had precious little information to go with. So we simply had to make do with what we could gain from various sources. Now, that means that we should be a bit careful with the interpretation of the numerical results, in particular when it comes to quantitative aspects of these. So the injection point we put in a fault that was very close to the bottom of the injection well. This was based on data from the well. In terms of boundary conditions, we have an idea of the regional stresses that we could use to set values for the poroelastic stress at the boundary. What we did not have was a stress history of the explicitly represented faults. That made initialization of the stress and the fault deformation model quite tricky. So for the fault, we assigned a static friction with a value that we could pull from the seismic analysis. For defining permeability values, the only information that we really had was this data from the leak-off test carried out just before the stimulation experiment. So that is not very much to go with. What is interesting is if you look at the induced seismicity up here and the location there of them. So it seems that more or less everything that happens takes place on the north side of this fault number 8. That is on the injection side of fault number 8. So a natural question to ask then is whether this could indicate that fault number 8 is a seal. So in order to investigate that, we devised 3 permeability cases. We got case number A, which is a fault. It corresponds to fault 8 being open and more or less equal in property to all the other fractures faults. We got case B, which is neutral, which it's almost as if fault number 8 was not there. And then there is case C, which is fault number 8 being sealing, and fluids will not easily go from the north to the south side of fault 8. With these cases and from the little data that we have available here, we then arrived at a set of parameters for permeability in the matrix and in the fault that at least are internally consistent. So I first show the pressure profiles obtained by the simulations. What is shown here is the pressure in the fault network. So there's also pressure diffusion into the rock matrix, but that is not shown for clarity reasons. What is more, we actually only show the pressure in a select few of the faults, again for reasons of clarity. Now, fault number 8 is this purple one here, and the figure is rotated a little bit so that the north side, the injection side of the fault, is then to the left and the south is to the right. Considering first the permeable case A, there is no special difference between the north and south side of fault 8, as you would expect, and we really see a very high pressure diffusion throughout the fault network. This is also the case, although to a slightly lower degree, for case number B, the neutral case, and you really need to go to case C, to the sealing fault 8, in order to isolate the pressure perturbation effect to the north side of fault number 8. So this is, as one would expect, there is, but it's still nice to see that the simulation results really reflect this intuition. Moving on now to the pore mechanical effects, which we measure in terms of the slip accumulated on the fault surfaces for the entire injection period. Now, these effects are much more difficult to interpret compared to that of the pure fluid pressure. The reason is that what we see is a combination of fluid pressure, which can migrate through the fault network and rock matrix, and that of stresses, mechanical stresses, which are transmitted through the rock matrix. Now, the former will feel the effect of fault 8 being open or sealing. The mechanical stresses will not. We see only a combination of these effects, and thus untangling what has really happened is rather challenging. Nevertheless, we have the 3 cases here. We have open, neutral, and sealing fault number 8. What is important to note here is the difference in color scales. So red here in the open case means much more slip compared to the closed case. So for the open and mainly also for the neutral case, there is, as expected, no real effect of this north-south boundary. There is slip throughout, and there is a lot of slip happening in the entire fraction network. For the sealing cases, it's different. We get this accumulation of focusing outer slip on the north side, and also to some degree in the region close to the injection. Now, if we then consider or compare this to the location of the observed seismic events, it is the sealing case which again shows the best fit to the observed seismicity. And so these simulation results then again indicate that fault number 8 seem to be have sealing properties. That said, there is quite there's a noticeable discrepancy between the simulation results and the observed seismic events. To conclude, we have successfully carried out a simulation study of the stimulation of a geothermal well. When compared with observations of seismics, the numerical results have certain similar features, but the match between observations and simulation results is honestly not striking. These discrepancies can be attributed partly to possible seismic sliding, but probably the main reason is wrong modeling assumptions and bad parameter values in the simulation model. This should then again be seen in the light of the relative scarcity of data that was available for populating the model. We have indicated the benefits from the simulation model, or having such a simulation model. It is easy to experiment with different parameter scenarios, and the model can also distinguish between sliding on faults that are very proximate and thus are difficult to distinguish in seismic observations. So our conclusion here is that this is one step towards simulation tools that are better honor this heterogeneity on the subsurface, which have then critical impact on these processes. Thank you for your attention.